This is what happens when you realize the universe you're living in is already, quietly, becoming a graveyard. Every star you can see tonight is a countdown clock, and most of the stars that have ever existed have already finished counting. If you've ever looked up and felt small, stick around, because it's about to get a lot bigger and a lot stranger than you think. Hit like and subscribe before we get into it, because where this goes next is going to change how you look at the night sky for good. Let's start with something most people never think about. When you look up at a clear night sky, you're not just looking at stars. You're looking at a mix of things still burning and things that have already died. And from Earth, without a telescope, you genuinely cannot tell which is which. A star that burned out 10,000 years ago can still appear to shine, because its light is still arriving. But that's not even the strange part. The strange part is what those dead stars actually become. Because a star doesn't simply vanish when it runs out of fuel. It leaves something behind. Astronomers call these leftovers stellar remnants, and there are 3 kinds, and which one you get depends entirely on how much mass the star started with. Before we even get to the 3 main types of stellar remnants, it's worth mentioning a 4th category that doesn't quite fit the pattern, because it never got the chance to. Not every collapsing cloud of gas actually makes it to being a real star. Some fall just short, and what's left is called a brown dwarf, sometimes nicknamed a failed star, an object heavier than the biggest gas giant planets but never quite massive enough, somewhere between about 13 and 80 times the mass of Jupiter, to ignite the ordinary hydrogen fusion that powers a true star. It can briefly burn a heavier, rarer form of hydrogen called deuterium, but that fuel runs out quickly, and after that, a brown dwarf simply cools and dims for the rest of its existence, never having burned brightly in the first place. The first one ever confirmed was found in 1994 and 1995, an object called Gliese 229b, spotted by a team of Caltech and Johns Hopkins astronomers, orbiting a small red dwarf star about 18 light-years from Earth. What confirmed it wasn't just its size. It was a very specific chemical signature in its light, bands of methane absorption, the exact kind of feature astronomers had previously only ever seen in the atmospheres of giant planets, never in anything resembling a star. For nearly 30 years afterward, Gliese 229b stayed slightly mysterious, because it was dimmer than its mass said it should be, an inconsistency nobody could fully explain. Then, in October of 2024, 2 separate teams using the Very Large Telescope in Chile finally solved it. Gliese 229b wasn't one brown dwarf at all. It was 2, locked in an extremely tight orbit around each other, separated by only about 16 times the distance between the Earth and the Moon, hiding in plain sight as a single object for 3 decades. Brown dwarfs like these don't really belong to the graveyard the way white dwarfs, neutron stars, and black holes do, because they were never technically alive to begin with. But when the universe eventually catalogs everything left over once the stars have gone out, this is exactly the kind of odd, half-lit object that gets filed right alongside them. If a star begins its life somewhere between about half the mass of our Sun and 8 times the mass of our Sun, it doesn't explode when it dies. Instead, it sheds its outer layers gently, puffing them off into space as a glowing cloud called a planetary nebula, and what's left behind is the exposed core of the star, a white dwarf. A white dwarf is a strange object once you sit with the numbers. It packs somewhere between 6/10 and 1.5 times the mass of the Sun into a sphere roughly the size of Earth. That means the material inside it is compressed to a density that has no everyday comparison. A teaspoon of white dwarf material would weigh several tons if you scooped it out and set it on a scale. And here's the detail that trips people up. More massive white dwarfs are actually smaller, not larger, because more mass means more gravity, and more gravity means more compression. It's the opposite of how we normally think about size and weight, where bigger usually means heavier, and heavier usually means bulkier too. Not here. Here, the more a white dwarf weighs, the tighter it squeezes itself into a smaller ball. What actually holds a white dwarf up against total collapse is something called electron degeneracy pressure, and it's worth explaining, because it's one of the strangest ideas in all of physics. Under normal conditions, electrons can be packed together fairly closely without much resistance, but in a white dwarf, Gravity is squeezing the electrons so tightly that quantum mechanics itself starts pushing back. There's a rule, baked into the fabric of reality, that says two electrons can never occupy exactly the same quantum state. So as gravity tries to cram them closer and closer together, the electrons are forced to move faster and faster just to stay distinguishable from one another. And that motion creates an outward pressure that has nothing to do with heat or ordinary physics, and everything to do with the electrons quite literally refusing to be identical. That pressure is strong enough to hold up an entire dying star. But it isn't infinite. There's a ceiling on how much mass a white dwarf can hold before this balancing act collapses entirely, and it was worked out by a young physicist named Subrahmanyan Chandrasekhar, who calculated it during a long sea voyage from India to England back in 1930. Picture that for a second. A 19-year-old on a ship, working through the mathematics of dying stars with pencil and paper somewhere in the middle of the ocean, arriving at a number that would end up defining the outer limit of what a stellar corpse can be. That number, close to 1.5 times the mass of the Sun, is now called the Chandrasekhar limit, and it marks the exact point where electron degeneracy pressure simply cannot win anymore. Push a dead star's core past that limit, and there's no more halfway measure. It collapses into something far more extreme. The story doesn't end with the calculation though, and it's worth knowing what happened next, because it's a genuinely rough one. In January of 1935, Chandrasekhar presented his findings at a meeting of the Royal Astronomical Society in London, and Arthur Eddington, at the time one of the single most influential astrophysicists alive, stood up and tore the young man apart publicly. He called the idea a stellar buffoonery, and argued there ought to be some law of nature specifically preventing a star from behaving that way. Several of the era's biggest names in physics, people like Niels Bohr, Paul Dirac, and Wolfgang Pauli, privately agreed that Chandrasekhar had the math right, but none of them were willing to publicly contradict a figure as towering as Eddington. The attacks continued for years, including at an international conference in Paris in 1939, where Chandrasekhar reportedly wasn't even given the normal chance to respond. Chandrasekhar himself, along with later historians looking back on the episode, has pointed to racial bias as part of what fueled the ferocity of it all. It took about 3 decades, and the actual observational discovery of neutron stars and black holes in the 1960s and 70s for the wider astrophysics community to fully accept that Chandrasekhar had been right the entire time, and Eddington had been wrong. In 1983, more than 50 years after doing the original math as a teenager on a boat, Chandrasekhar finally received the Nobel Prize in Physics for it. By then, it was simply accepted science, the same limit taught to every astronomy student today, the same one already sitting quietly underneath everything else in this video. That brings us to the second kind of remnant. Stars that start out somewhere between roughly 8 and 20 times the mass of the Sun don't fade quietly the way smaller stars do. They go out in a supernova, a titanic explosion that blows the outer layers of the star into space at incredible speed, while the core, left behind, collapses down into a neutron star. A neutron star crams somewhere between 1.5 and 3 solar masses into a sphere only about 10 kilometers across, which is roughly the size of a city. Not a planet, not a moon, a city. At that point, gravity has crushed the matter so hard that protons and electrons have literally merged together into neutrons, and the star is held up not by electron degeneracy pressure anymore, but by an even more extreme version of the same basic idea, called neutron degeneracy pressure, a quantum mechanical resistance that only kicks in at densities that make a white dwarf look almost fluffy by comparison. You don't have to take this on faith either, because there's a star doing this right now, close enough that you can go outside tonight and look at it with nothing but your own eyes. Betelgeuse, the reddish star marking Orion's shoulder, sits somewhere between about 550 and 640 light-years away, and it is enormous, roughly 1,000 times wider than our Sun, big enough that if you dropped it into the center of our solar system, its outer surface would reach somewhere close to Jupiter's orbit. It is, by every measure astronomers use, a star in the late stages of exactly the process we just described, headed toward a supernova and a neutron star or black hole of its own, though the timeline for that remains wide open, anywhere from relatively soon to as much as 100,000 years from now. In late 2019 and into early 2020, Betelgeuse dimmed dramatically, dropping to something like 40% of its usual brightness. And for a while, the entire astronomy world wondered if this might be the beginning of the end. It wasn't, at least not yet. Follow-up research found the dimming was caused by a combination of a large, cooler patch on the star's surface and a genuinely enormous eruption, in which Betelgeuse blew off part of its own visible surface, ejecting something like 400 billion times the mass of a typical solar eruption in one single event. More recently, in 2024 and 2025, astronomers confirmed something else entirely was going on. Betelgeuse has a small companion star, nicknamed Sawaha, quietly orbiting it roughly every 5.5 years, stirring up the gas in its outer atmosphere as it goes, which explains a lot of that mysterious flickering that had people worried in the first place. And in case you're wondering, even when the real explosion eventually comes, we're in no danger. Studies suggest a supernova would need to happen within about 160 light-years to actually threaten Earth, and Betelgeuse sits roughly 4 times that distance away. It's not a warning sign, it's just a preview, playing out in real time, of exactly the kind of stellar death this section has been describing the whole way through. And then there's the third path. Push a star's starting mass above roughly 20 times the Sun's mass, and when it finally exhausts its fuel and collapses, there is no pressure known to physics, not electron degeneracy, not neutron degeneracy, nothing that can stop it. Gravity wins completely, and the result is a black hole, an object so dense that not even light, the fastest thing in the universe, can escape its pull once it crosses a certain boundary. These 3 outcomes, white dwarf, neutron star, black hole, aren't rare exceptions carved out for a handful of unusual stars. They are the ordinary, expected ending for nearly every star that has ever burned, which means the galaxy around us isn't just theoretically full of stellar remains somewhere out there in the abstract. It's actually littered with the bodies of stars that finished burning long before humans existed, and in plenty of cases, long before Earth itself even formed. Even the name itself has a specific birthday, and it's a lot more recent than the concept. The underlying idea actually stretches back to 1783, when an English clergyman named John Mitchell reasoned that an object dense enough could have gravity so strong that not even light could escape it, making it effectively invisible, a dark star, in his own words, more than a century before Einstein was even born. Carl Schwarzschild worked out the actual mathematics in 1916, just months after Einstein published general relativity. And for decades after that, even Einstein himself was skeptical such an object could really exist in nature rather than just on paper. The phrase black hole itself didn't show up until December of 1967, coined, or at least popularized, by physicist John Archibald Wheeler, and here's the detail worth sitting with. Wheeler introduced the term at a conference specifically about pulsars at NASA's Goddard Institute in New York, only months after Jocelyn Bell Burnell's original pulsar discovery back at Cambridge. He'd been trying to describe a gravitationally completely collapsed object and found the phrase too clunky to keep repeating, and when someone in the audience suggested black hole instead, it struck him, in his own words, as exactly right, which means the 2 threads of this section, the blinking dead stars and the invisible ones, are tied together by more than just theme. They share an actual birthday, a few months apart, in 1967. Some neutron stars announce themselves in a way nothing else in the graveyard does, and the story of how we found out is worth telling properly. In November of 1967, a 24-year-old graduate student at Cambridge named Jocelyn Bell was scanning through rolls of chart paper produced by a radio telescope she had personally helped build, 120 miles of wire strung across wooden poles in a field outside the city. Buried in the data, taking up barely a fraction of an inch across meters and meters of paper, she noticed something odd, a signal repeating with almost impossible regularity, about once every 1.3 seconds, over and over, precise enough that it initially seemed less like a star and more like a machine. She and her supervisor, Anthony Hewish, half-jokingly nicknamed the source LGM-1 for Little Green Men, not because they seriously believed it was an alien transmission, but because they needed some kind of shorthand while they figured out what it actually was. Bell soon found more of these signals coming from entirely different parts of the sky, which ruled out anything artificial or local. And what she had actually discovered was a pulsar, a neutron star spinning incredibly fast, sweeping a beam of radio waves past Earth, like a lighthouse with every rotation, so precisely timed that it can be used, even today, as one of the most accurate clocks in the known universe. That first pulsar, now catalogued as PSR B1919+21, is a dead star, a genuine resident of the graveyard we've been describing, just one that happens to blink. The discovery won the Nobel Prize in Physics in 1974. It went to Hewish. Belle Burnell, the person who actually found it, staring at that fraction of an inch of chart paper until her brain refused to let it go, was left off the prize entirely, a decision that's been debated in the astronomy community for decades since. Here's the thing though, people had actually seen a star like this die once before, 900 years earlier, with nothing but their own eyes. On or around July the 4th, in the year 1054, a new star suddenly appeared in the constellation Taurus, bright enough to be seen in broad daylight for 23 straight days, and visible at night for roughly 2 years afterward. Chinese court astronomers recorded it carefully as a guest star, one of 75 such events they catalogued across more than 1,500 years of continuous skywatching. Japanese records mention it. Arab astronomers noted it. There's even a rock carving in present-day New Mexico associated with the ancestral Puebloan people that some researchers believe depicts the very same event. None of these observers had telescopes. None of them had any concept of nuclear fusion, or degeneracy pressure, or the Chandrasekhar limit. They just knew that a bright new light had appeared in the sky where nothing had been before, and that it eventually faded. What they were actually watching, without any way of knowing it, was a massive star ending its life in a supernova. The wreckage of that explosion is still there today, a glowing, expanding cloud of gas astronomers now call the Crab Nebula, first spotted through a telescope in 1731, and only connected back to that medieval guest star in the 1920s and 1940s. And sitting at the very center of that nebula, spinning and blinking exactly the way Jocelyn Bell would eventually discover such things could, is a real, confirmed neutron star, the Crab Pulsar, found in 1968. Which means the entire arc of this story, from a 900-year-old naked eye observation to a graduate student's chart paper to everything we've walked through tonight, comes back to the exact same object, a massive star, dying, leaving behind a small, spinning, impossibly dense corpse that people have now been watching, one way or another, for nearly 1,000 years. Here's where it gets personal, because the Milky Way isn't just vaguely, distantly full of dead stars. Researchers estimate there are something like 100 million stellar mass black holes scattered throughout our own galaxy. 100 million. Sit with that number for a second, because it's not a number from some other galaxy far away. It's the galaxy you live in, right now, tonight. And the overwhelming majority of those black holes are completely invisible, because a black hole with nothing falling into it emits no light at all. It doesn't glow, it doesn't flicker, it just sits there, doing nothing but bending the space around it. And the only way we ever find one is almost by accident, by watching how it tugs on something we actually can see. And some of those dead objects aren't scattered randomly at all. They're clustered together, densely, in structures so old that astronomers had to invent a specific term for what they'd found. Globular clusters are tightly packed spherical swarms of hundreds of thousands of stars, and they rank among the oldest structures in the entire galaxy, orbiting outside the Milky Way's younger, flatter disk like ancient satellites. One of them, called NGC 6397, sits roughly 7,000 to 8,000 light-years away in the constellation Ara, and it clocks in at about 13.4 billion years old, meaning it started forming shortly after the Big Bang itself. In 2004, a team of astronomers measured the beryllium content inside 2 of its stars, using that chemistry to work backward and estimate the age of the entire Milky Way galaxy at roughly 13.6 billion years, remarkably close to independent estimates for the age of the universe as a whole, which sit around 13.7 to 13.8 billion years. Separately, Hubble Space Telescope observations of the ancient white dwarfs buried inside a nearby cluster called M4 dated those dead stars at somewhere between 12 and 13 billion years old, giving astronomers yet another independent cross-check on the age of everything, using nothing more than the physics of cooling stellar remnants. And here's the detail that ties this section together with almost eerie precision. In 2022, a team of astronomers studying the black holes and other compact dead star remnants packed into the centers of clusters like NGC 6397 published their findings in a real, peer-reviewed scientific journal under a title that could have been lifted directly from this video. They called it, literally, stellar graveyards. Not as a dramatic flourish for a documentary script, as an actual technical term used by working astrophysicists to describe exactly the kind of dense, ancient clustering of dead stars that NGC 6397 turned out to have at its core. That's exactly how astronomers found the closest known black hole to Earth. It's called Gaia BH1, and it sits about 1,560 light-years away from us, in the direction of the constellation Ophiuchus. It was discovered in 2022 by a team led by astronomer Kareem El-Badri, working with the Center for Astrophysics at Harvard and Smithsonian, along with the Max Planck Institute for Astronomy. They didn't see the black hole directly, because you can't, not really. What they saw was a star remarkably similar to our own sun, wobbling in its orbit in a way that made no sense unless something massive and completely dark was pulling on it from nearby. It's a bit like watching a dance partner spin and dip on a stage where the other dancer is invisible. You never see the second dancer. You just see the first one moving in ways that only make sense if someone else is there, holding their hand. Follow-up observations using multiple telescopes around the world confirmed it. That companion star orbits the black hole roughly every 185 days, at a distance close to the gap between Earth and our own sun. Picture that for a second. Take our solar system, swap the sun for a black hole nearly 10 times its mass, and swap Earth for a sun-like star, and you've basically rebuilt the Gaia BH1 system, sitting quietly in our own galactic backyard. Gaia BH1 is what astronomers call dormant. It has no accretion disk, meaning it isn't actively pulling in and devouring surrounding gas, which is part of why it went undetected for so long. If it were feeding, actively tearing matter apart and heating it to the point of glowing, we would have spotted it far sooner, the way most black holes discovered before it were found, by their appetite, not their absence. And before you start worrying about it, the numbers make it clear this thing poses zero danger to us. Even traveling at the fastest speeds our current spacecraft can manage, it would take roughly 40 billion years to reach it. That's longer, by a wide margin, than the entire current age of the universe, which is about 13.8 billion years. It's not close in any way that matters for us. It's just close on a galactic scale, which tells you everything about how vast and how empty even a graveyard really is. And Gaia BH1 wasn't a one-off discovery. The same team went on to find Gaia BH2, roughly 3,800 light-years away in the constellation Centaurus, orbiting a red giant star instead of a sun-like one. Then came Gaia BH3, sitting somewhere around 1,900 light-years out, and this one is a genuine heavyweight, weighing in at about 33 times the mass of the Sun, making it the most massive stellar black hole ever found inside the Milky Way. All three were found using data from the European Space Agency's Gaia spacecraft, a mission that spent over a decade, from 2014 until 2025, meticulously tracking the positions and motions of over 1 billion stars. It wasn't designed to hunt black holes specifically. It found them anyway, simply by noticing which stars were wobbling for no visible reason, the same way you might notice a rope swaying and realize someone invisible must be tugging on the other end. And it's not just that the graveyard is nearby, it's also almost as old as time itself. While Gaia was busy finding sleeping black holes practically in our own backyard, a completely different instrument, the James Webb Space Telescope, was busy finding the opposite kind of black hole. Not close, but ancient, sitting at the very edge of what it's possible to see at all. Because light takes time to travel, looking far enough away is the same thing as looking far enough back in time, and in January of 2024, astronomers using Webb announced they'd found the oldest, most distant black hole ever observed, sitting at the center of a galaxy called GNZ11. That black hole, weighing in at around 1.6 million times the mass of the Sun, existed just 400 million years after the Big Bang. The light reaching Webb's mirrors when astronomers captured that image, had been traveling for roughly 13 billion years to get there. Other black holes found by Webb since then push the timeline back even further, some existing within the first 500 million years after the Big Bang. And in 2024, astronomers even caught two supermassive black holes in the act of merging, in galaxies colliding just 740 million years after the universe began. These black holes are so early and grew so unbelievably fast that they've become one of the biggest open puzzles in modern astrophysics. Nobody currently has a fully satisfying explanation for how something can get that massive that quickly. But the bigger point for our purposes is simpler than the puzzle itself. This graveyard we've been describing isn't a recent development. It didn't start with dying stars near Earth. It's been under construction since almost the very beginning of the universe's history, practically since the lights first turned on. And it isn't only light that tells us this graveyard is out there either. Sometimes we don't see it. We feel it, or at least our instruments do. On September the 14th, 2015, two enormous detectors, one in Hanford, Washington, one in Livingston, Louisiana, each with arms miles long, picked up an almost impossibly faint tremor passing through the fabric of space itself. It was the first direct detection in human history of a gravitational wave, a ripple in space-time that Albert Einstein had predicted a full century earlier, but that nobody had ever actually managed to catch. The source turned out to be two black holes, one about 36 times the mass of the Sun, the other about 29 times the mass of the Sun, spiraling into each other and merging into a single black hole roughly 62 times the Sun's mass, some 1.3 billion light-years away. Do the math on those numbers for a second. 36 plus 29 adds up to 65, but the black hole left behind only weighed 62. The missing 3 solar masses hadn't vanished. They had been converted directly into raw energy and blasted outward as gravitational waves, and for a fraction of a second, that single collision released more power than the combined light of every star in the observable universe. By the time that signal finished crossing 1.3 billion light-years of space and reached Earth, it had weakened to a disturbance thousands of times smaller than the width of an atomic nucleus, and our instruments still caught it. The scientists behind that detector, Rainer Weiss, Barry Barish, and Kip Thorne, won the Nobel Prize in Physics for it in 2017. And what was once one of the rarest, most celebrated observations in the history of physics has since become almost routine. Today, that same detector, working alongside partner observatories in Italy and Japan, picks up a black hole merger somewhere in the universe roughly once every 3 days. The graveyard, it turns out, isn't silent. It's constantly humming with the sound of collisions we only just recently learned how to hear. Black holes aren't the only ghosts drifting through the galaxy either. There's a whole other category of wandering object out there, one that used to belong to a star and doesn't anymore. Rogue planets, sometimes called free-floating planets. Worlds that have been ejected entirely from whatever system they were born in and now drift alone through interstellar space with no star to orbit at all. And here's an honest admission worth making, because it's more interesting than pretending we have a precise head count. Nobody actually agrees on how many of these things exist. A 2011 survey, led by astronomer Takahiro Sumi, suggested there might be roughly 2 Jupiter-sized rogue planets for every single star in the galaxy. Then, in 2017, a different team, led by Przemek Mróz, publishing in the journal Nature, revised that estimate sharply downward to something closer to a quarter of a rogue planet per star. Meanwhile, a 2012 study out of Stanford's Kavli Institute estimated that much smaller, lower-mass wandering objects could outnumber stars by as much as 100,000 to 1, once you count everything down to roughly the size of Pluto. Other more recent work, cited by researchers including David Bennett at NASA's Goddard Space Flight Center, has landed somewhere in between, suggesting the Milky Way could be home to trillions of rogue worlds. These estimates disagree with each other by orders of magnitude, and that's not a flaw in the storytelling. It's an honest snapshot of where the science actually stands right now. Nobody has taken an actual census. It's genuinely still an open question. What isn't in question is that these worlds are real, and we've started to actually pin some of them down. In a paper published in the journal Science on January 1st, 2026, a team led by Subo Dong of Peking University announced the very first rogue planet with both a directly measured mass and a directly measured distance. It began as a tiny 2-day flicker of light from a distant star near the galactic bulge, caught back on May 3, 2024, an event later catalogued under the names KMT 2024 BLG-0792 and OGLE 2024 BLG-0516. That flicker turned out to be the gravitational fingerprint of an unseen planet passing in front of the star, bending its light just enough to notice, a technique called microlensing. The object it revealed sits roughly 9,800 light-years away and carries about a fifth of the mass of Jupiter, putting it on par with Saturn. A whole planet, once part of a functioning solar system somewhere, now drifting utterly alone through the galaxy, detectable only because it happened to pass in front of exactly the right star at exactly the right moment for us to catch it. However many of these worlds are actually out there, whether it's billions or trillions, every single one of them is a small, cold reminder that stars don't just leave behind corpses when they die. They can also cast their own children out into the dark, long before or long after the star itself is gone. So that's the graveyard around us right now, quietly scattered through the galaxy, mostly invisible, occasionally betrayed by the gravitational tug it leaves on a nearby star or a distant flicker of light. But here's the part that makes this less of an abstract astronomy lesson and more of a personal one. Our own sun, the star every single one of us depends on for literally everything, is going to join that graveyard too. It's not a question of if, it's only a question of when, and the timeline is better understood than you might expect. Right now, the sun is about 4.57 billion years old, which puts it just about halfway through its expected lifespan as a stable, hydrogen-burning star. For roughly another 5 billion years, give or take, it will keep doing what it's doing now, fusing hydrogen into helium in its core, releasing the light and heat that makes life on Earth possible. But that stability has an expiration date. Once the hydrogen fuel in its core runs low, in something like 5 to 5.5 billion years from now, the sun's core will start to contract, while its outer layers dramatically expand. The sun will balloon into a red giant, growing to something like 256 times its current size. At that scale, it will almost certainly swallow Mercury and Venus whole. There simply isn't anywhere for those planets to go. And this isn't just theoretical either. We've actually caught a planet somewhere else in the galaxy being eaten in real time, which is about as close as astronomy gets to catching the future red-handed. Roughly 600 light-years away, in the constellation Auriga, there's a gas giant called WASP-12b, discovered back in 2008, orbiting so close to its star that a full year there lasts a little over 1 Earth day. In May of 2010, the Hubble Space Telescope watched that planet's atmosphere get stretched into the shape of a football by its star's gravity, ballooning out to nearly 3 times the size of Jupiter, and quite literally spilling material directly onto the star's surface, like water pouring off the edge of an overfilled glass. The planet has been superheated to nearly 2,800 degrees Fahrenheit. Astronomers estimate it has somewhere between 3 and 10 million years left before it's fully consumed, making it possibly the shortest-lived known planet in the entire Milky Way. Nobody had to imagine what a star eating a planet looks like. We turned a telescope in the right direction and watched it happening. Earth's fate is the part scientists genuinely disagree on, and it's worth being honest about that instead of pretending it's settled. Some models suggest Earth might get pulled just far enough away as the sun sheds mass and its gravity weakens to avoid being swallowed outright. Other models suggest it won't be so lucky. Either way, whether Earth survives as a scorched, drifting husk or gets consumed entirely, the outcome for anything living here is the same: uninhabitable, long before that final chapter even plays out. And here's the detail that should really land. The real deadline isn't the sun's death at all. It's much sooner than that. The sun's energy output has been slowly climbing this whole time, growing roughly 10% brighter every billion years. And within about 1 billion years from now, that extra heat alone will be enough to boil away Earth's oceans and end the story for life here, long before the sun ever becomes a red giant. Read that again if you need to. 1 billion years for the oceans, 5 billion years for the sun itself. We are not waiting on the dramatic ending. The quiet ending arrives first. And this isn't purely theoretical guesswork either. In 2024, astronomers at UC Berkeley, using the Keck Observatory in Hawaii, actually found a real example of what Earth's best-case outcome might look like. Roughly 4,000 light-years away, in a system near the center of our galaxy, they spotted a white dwarf, a dead star about half the mass of our Sun, with an Earth-sized planet orbiting it at roughly twice the distance Earth currently sits from our own Sun. It was found almost by chance, when the planetary system passed in front of a more distant star back in 2020, and briefly magnified that star's light. The discovery matters because it shows this outcome is genuinely possible, not just mathematically plausible. A rocky, Earth-sized world that survived its star's entire red giant phase got pushed outward into a wider, colder orbit as the dying star lost mass, and ended up quietly circling the dim, cooling corpse left behind. Nobody thinks that particular planet is habitable anymore, sitting that far out from a dead star's leftover glow, but it is, in the plainest sense, a snapshot of a solar system roughly 8 billion years further along a path our own solar system may or may not survive. After spending around 1 billion years puffed up as a red giant, the Sun will begin shedding its outer layers into space, forming a glowing shell of gas called a planetary nebula, the same kind of structure we see today around other dead stars, like the well-known Ring Nebula. What's left behind at the center, once that shedding is done, is the Sun's true final form, a white dwarf, holding on to roughly half its original mass, but packed into a body smaller than Earth is right now. From there, it doesn't explode, and it doesn't do anything else dramatic. It simply cools, slowly, for an almost incomprehensible stretch of time. But here's a detail most people have never heard, and it's one of the strangest, most beautiful facts in this entire story. In January of 2019, astronomers using data from that same Gaia spacecraft analyzed roughly 15,000 white dwarfs within about 300 light-years of Earth, and found something that had only ever been predicted, never observed. A kind of traffic jam in the data, a pile-up of white dwarfs at very specific colors and brightness levels that shouldn't have been there. It turned out that pile-up was direct evidence of something theorized 50 years earlier, back in 1968, but never actually confirmed until Gaia caught it. White dwarfs, as they cool, don't just fade quietly forever. Their cores, made of carbon and oxygen, eventually solidify. They crystallize. The dead star, at the very end of its long cooling process, essentially turns into an enormous crystal floating in space. As it crystallizes, it releases a burst of stored heat, which is what created that unexpected pileup in the data. Oxygen crystallizing first and sinking toward the center, pushing carbon upward in a process not unlike sediment settling on a riverbed, releasing gravitational energy in the process and slowing the cooling down even further. Pierre-Emmanuel Tremblay, the astronomer at the University of Warwick who led that discovery, put it in the plainest terms possible. The Sun itself, he said, will become a crystal white dwarf in about 10 billion years. Not metaphorically, not poetically. Our Sun, the thing keeping you alive right now as you listen to this, is on a 10 billion year path toward literally becoming a giant, dim, Earth-sized crystal, drifting through whatever the galaxy looks like by then. Given long enough after that, trillions of years, far beyond even the current age of the universe, that crystallized white dwarf would theoretically cool all the way down into what's called a black dwarf, a cold, dark, dead ember of carbon and oxygen drifting silently through space, giving off no meaningful light or heat at all. And here's a detail worth sitting with. No black dwarfs exist anywhere in the universe yet, not one, because the universe simply isn't old enough. The process takes longer than 13.8 billion years allows for. Every white dwarf that has ever formed, everywhere, in every galaxy, is still cooling. The graveyard hasn't even finished its first generation of headstones. While all of that is happening to our star specifically, something much larger has, for decades, seemed to be closing in on our galaxy as a whole. The Andromeda Galaxy sits about 2.5 million light-years away, and it happens to be the most distant object you can see with the naked eye. It is also, right now, racing toward us, closing the distance at somewhere around 110 to 116 kilometers every single second. For decades, based on detailed Hubble Space Telescope data released in 2012, astronomers described a head-on collision between the Milky Way and Andromeda as essentially inevitable, arriving in about 4 billion years and fully merging into one giant elliptical galaxy, sometimes nicknamed Milkomeda, around 6 billion years from now. Andromeda alone contains something like 1 trillion stars. Our own Milky Way holds around 300 billion. And yet, because stars are spaced so incredibly far apart, actual star-on-star collisions during this merger are considered extremely unlikely. The two galaxies would essentially pass through one another, flinging some stars into new orbits, without individual stars actually smashing together. Eventually, the supermassive black holes, sitting at the very center of each galaxy, are expected to spiral toward one another and merge as well. But here's where the story gets more interesting and more current. Newer research, using more than a decade of additional Hubble data combined with precision measurements from the Gaia spacecraft, has actually walked that certainty back. A reanalysis found only about a 50-50 chance of a genuine, direct collision within the next 10 billion years, once you properly account for the gravitational influence of smaller nearby galaxies like the Large Magellanic Cloud. There's still a small chance, somewhere around 2%, of a true head-on collision, specifically within 4 to 5 billion years. In other words, the thing astronomers spent a century treating as an inevitable cosmic collision might not even happen the way we assumed. But none of that changes the bottom line for us. Whether or not Andromeda and the Milky Way ever actually collide, our Sun will have already made Earth uninhabitable in about 1 billion years, and the Sun itself will likely be dead within about 5 billion years. The galactic collision, if it even happens, is the least of our problems. Before we go any further, it's worth pausing on just how big the thing we're actually describing is, because even that number keeps changing. Ask an astronomer how many galaxies exist in the observable universe, and depending on which decade you asked, you'd have gotten a wildly different answer. Back in 1999, the best estimate was around 125 billion. By 2013, that had climbed to around 225 billion. Then, in October of 2016, a team led by Christopher Consolis at the University of Nottingham took 20 years of accumulated Hubble Space Telescope images, converted them into three-dimensional models, and revised the number upward by a factor of 10, all the way to roughly 2 trillion galaxies, most of them small, faint, and completely undetected by any telescope we currently have. Consolis's own conclusion was almost dizzying. Based on that math, over 90% of all the galaxies in the observable universe have never actually been directly seen by anyone. Since then, some researchers have argued the real number could be even higher, 6 trillion, maybe 20 trillion, extrapolating from how many small satellite galaxies cluster around larger ones like our own Milky Way. And then, in 2021, a study using NASA's New Horizons spacecraft, the same probe that flew past Pluto, took advantage of its position far outside the glare and light pollution of our inner solar system to directly measure the total background glow of the sky, and came back with a much more modest figure, suggesting the true number might actually sit closer to that older estimate of 100 to 200 billion after all. As of right now, astronomers will tell you, honestly, that the real answer is somewhere between 2 trillion galaxies at the high end and 100 billion at the low end, and nobody can currently narrow that gap any further. That's not a minor rounding error. That's an uncertainty spanning a factor of 20, in the most basic possible question you could ask about the size of the graveyard this entire video is describing. And it's worth sitting with that for a second, because it says something honest about where this field of science actually stands. We're not looking at a finished picture. We're looking at a live one, still being sketched in, decade by decade, telescope by telescope. Space is one way to lose your footing in a story like this. Time is the other, and it might actually be the harder one to hold on to. Carl Sagan came up with a trick for it back in the 1970s, something he called the cosmic calendar. And it's worth borrowing here before we go any further into the future, because you need a feel for the past first. Take the entire 13.8 billion year history of the universe and squeeze it down into a single calendar year. The Big Bang happens in the first instant of January the 1st. This exact moment, you, listening to this, happens in the final instant of December the 31st. On that scale, a single cosmic second works out to about 438 real years. A cosmic hour is about 1.6 million real years. Our galaxy, the Milky Way, doesn't even form until sometime around March. The Sun and the Earth don't show up until early September. Dinosaurs don't appear until December the 25th, and they're already gone before the calendar year is out. And every single thing you have ever read in a history book, every empire, every war, every name anyone has ever bothered to write down, fits inside the final 14 seconds before midnight on December the 31st. 14 seconds out of an entire year. Sagan liked to point out that first contact between the civilizations of Europe and the Americas, an event that reshaped the entire planet, happened with less than 2 seconds left on the clock. He called the whole exercise a humility instrument, something built specifically to break the quiet, unconscious assumption that human timescales are somehow the natural scale of the universe. And here's the part that actually matters for the rest of this video. Everything that calendar just described, the entire 13.8 billion years from the Big Bang to right now, to this sentence, is the past. It's already happened. It's the shortest, fastest moving part of this entire story. Every future era we're about to walk through, the slow fade of the stelliferous era, the 100 trillion years, the degenerate era stretching out past 10 to the 39th years, the black holes finally evaporating past 10 to the 100th years, would need a calendar so large that Sagan's entire one-year version, Big Bang to right now, wouldn't even register as a single tick of a single second on it. We're not just small in space. We're standing at the very beginning of something almost incomprehensibly long and calling ourselves late to the party. Before we zoom out any further, there's one more thread worth pulling on, because it's the most human detail in this entire story. Right now, 2 machines built by our own species are already out there, already headed into that same long future. Voyager 1 and Voyager 2 launched in 1977, and they are, at this point, the most distant human-made objects that exist. Voyager 1 sitting about 25 billion kilometers from Earth. Voyager 2 not far behind it, both of them having already crossed the boundary of the Sun's solar wind and entered true interstellar space. They run on the heat of slowly decaying plutonium, losing about 4 watts of power every single year. And NASA engineers have spent the last several years carefully shutting down instrument after instrument just to keep the 2 spacecraft breathing a little longer, hoping to reach their 50th anniversary in 2027, aware that any given day could be the last time either one calls home. Eventually, and it could be soon, the power will run out completely, and both Voyagers will go silent for good. But going silent isn't the same as stopping. A physicist named Nick Oberg actually modeled out what happens to these 2 machines after that, tracking their trajectories forward across timescales that make everything else in this video look brief by comparison. And depending on how much interstellar dust slowly erodes them along the way, he found the Voyagers could conceivably keep drifting for something on the order of trillions of trillions of trillions of years. In his own words, describing that future, the probes will be drifting through what would be, to us, a completely unrecognizable galaxy, free of what we'd call ordinary stars, populated almost exclusively by black holes and stellar remnants like white dwarfs and neutron stars. 2 machines built by people who lived their entire lives on a single small planet, in a single narrow slice of cosmic time, could end up outlasting not just humanity, not just Earth, not just the Sun, but very possibly every star currently shining anywhere in the sky tonight. And it's worth being specific about exactly what those 2 machines are actually carrying with them into that far future, because it's not just scientific instruments. Bolted to each spacecraft is a gold-plated copper phonograph record, put together by a committee led by Carl Sagan over the better part of a year. On it, a little over 100 photographs of Earth and human life, encoded so that anyone capable of building a record player could, in theory, decode them. Sounds of wind, rain, ocean surf, thunder, a chimpanzee, crickets, footsteps, laughter, a human heartbeat, and, after some trial and error involving one very unconvincing attempt by a sound engineer kissing his own arm, an actual kiss. 90 minutes of music. Bach, Beethoven, Mozart, Chuck Berry's Johnny B. Good, blues, and traditional songs from cultures all over the planet. Spoken greetings in 55 different languages. The very first one from the Secretary General of the United Nations. The very last one, in English, recorded by Carl Sagan's own 6-year-old son, Nick, who simply said, "Hello from the children of planet Earth." Ann Druyan, The record's creative director, who would go on to marry Sagan, even had her own heartbeat and brainwaves recorded on an EEG machine for a full hour, compressed down to about a minute of sound, and by her own later admission, she spent part of that session thinking about the two of them, having gotten engaged only days before. There is, quite literally, a fragment of somebody falling in love, encoded onto a golden record, currently drifting through interstellar space. Sagan himself put the purpose of the whole thing simply. The spacecraft will only ever be found, he said, if there are advanced spacefaring civilizations out there to find it. But launching that bottle into the cosmic ocean says something very hopeful about life on this planet. That record was engineered to remain playable for up to 1 billion years. Compared to the trillions of years Voyager itself might actually keep drifting, even 1 billion years is barely the opening moment. They would drift on, carrying that golden record, a heartbeat, a kiss, a child's voice, through a galaxy that no longer has anyone left to send them anywhere or to receive them. Now zoom out, way out, past our galaxy, past Andromeda, past everything we can currently see, and ask a bigger question. What happens to the entire universe over the full span of time it has left? This is where two astrophysicists, Fred Adams from the University of Michigan and Gregory Laughlin from UC Santa Cruz, come in. In 1997, they published a paper called A Dying Universe in the journal Reviews of Modern Physics, and 2 years later, they expanded it into a book called The 5 Ages of the Universe. What they did was take everything known about physics and cosmology and use it to sketch out the entire future of the universe, broken into 5 distinct eras. And because the timescales involved get so enormous, so quickly, they didn't measure time in years. They measured it in what they called cosmological decades, where each step up represents a power of 10. A cosmological decade of 6 means 10 to the 6th power, or 1 million years. A cosmological decade of 100 means 10 to the 100th power, a number so large it barely means anything intuitively, but we'll get there. The first era, the primordial era, covers everything from the instant of the Big Bang up through roughly the first 100,000 years, when the universe was a hot, dense soup of radiation and elementary particles slowly cooling into atoms. We actually have a direct, physical fingerprint left over from near the end of that era, and it was discovered completely by accident. Back in 1964 and 1965, 2 radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were using an extremely sensitive horn-shaped antenna, originally built for satellite communication, and they kept picking up a strange, faint hiss of microwave noise. It came from every direction in the sky, equally, no matter where they pointed the antenna, day or night, in every season. They assumed it was equipment trouble. They ruled out interference from New York City. They ruled out radiation from the Milky Way. At one point, they even climbed into the antenna itself and physically scraped out pigeon droppings, thinking the birds nesting inside might somehow be responsible. The noise never went away. Eventually, they learned that physicists elsewhere had theorized that if the Big Bang really happened, it should have left behind a faint bath of leftover radiation, stretched out and cooled by billions of years of cosmic expansion, filling the entire universe evenly in every direction. That's exactly what they had stumbled onto. Astronomers now call it the cosmic microwave background, and it's essentially the oldest light in existence. Relic radiation from roughly 300,000 years after the Big Bang, cooled by the universe's expansion from an original temperature of around 3,000 degrees Kelvin down to a frigid 2.725 degrees today, just a couple of degrees above absolute zero. Penzias and Wilson won the Nobel Prize in Physics for it in 1978. Every time you point an old analog television at a dead channel and see static, a tiny fraction of that static, historically, was this exact radiation. You were watching the afterglow of the birth of the universe, and nobody knew it. Decades later, that same faint afterglow got measured with a precision Penzias and Wilson could never have dreamed of. Between 2009 and 2013, the European Space Agency's Planck satellite mapped the cosmic microwave background in extraordinary detail. Its instruments cooled to within 1/10 of a degree of absolute zero, just so it could detect temperature differences across the sky as small as 1/1,000,000th of a single degree. When the results came out in March of 2013, they nudged the age of the universe upward to 13.82 billion years, about 100 million years older than scientists had previously calculated, simply because the new data showed the universe expanding slightly more slowly than earlier estimates assumed. Planck also refined the universe's ingredient list, roughly 4.9% ordinary matter, the stuff that makes up stars, planets, and every person who has ever lived, roughly 26.8% dark matter, and roughly 68.3% dark energy, that same mysterious force we're about to spend the rest of this video unpacking. And here's an honest wrinkle worth mentioning, because it's still unresolved as of right now. Different methods of measuring exactly how fast the universe is expanding don't agree with each other. Measurements based on the cosmic microwave background put the expansion rate at around 67 kilometers per second per megaparsec. Measurements based on nearby standard candles, the same kind of exploding stars we'll get to in a moment, put it closer to 73. Nobody currently has a confirmed explanation for the gap. Astronomers call it the Hubble tension, and it's a live, open problem, a reminder that even a number as basic as the age of the universe itself, the number this entire video is built on top of, is still being actively measured, argued over, and refined, not handed down from on high as some finished, settled fact. We're not living in that primordial era anymore, obviously. We're in the second one, the stelliferous era, meaning, quite literally, filled with stars. This is the era we're living in right now, the one defined by galaxies, star formation, and everything we typically picture when we imagine the universe. According to Adams and Laughlin's framework, this era doesn't end for a long time yet, stretching out until roughly 100 trillion years after the Big Bang. That's when galaxies will have finally run out of the hydrogen gas needed to form new stars, and even the slowest, most fuel-efficient stars, the small, dim red dwarfs that can burn for unbelievably long stretches, will finally flicker out. Once that happens, star formation is over, permanently. The universe transitions into its next chapter. That next chapter is called the degenerate era, and this is where things start to feel genuinely alien. With no new stars forming, the ordinary matter left in the universe is now almost entirely locked up in those dead stellar remnants we talked about earlier: brown dwarfs, white dwarfs, neutron stars, and black holes. Adams and Laughlin even joke, in their own writing, that degenerate here refers to a quantum mechanical state of matter, not a moral judgment. This era is expected to stretch across an unbelievable range of time, roughly from 10 to the 15th power of years, out to somewhere around 10 to the 39th power of years. During part of this stretch, some models suggest white dwarfs might generate a trickle of extra energy from the annihilation of dark matter particles passing through them, but that particular fuel source is expected to run dry by around cosmological decade 30. After that, if certain predictions from particle physics turn out to be correct, protons themselves, the very building blocks of atomic matter, start to decay, slowly converting the remaining mass of white dwarfs and neutron stars directly into radiation. A white dwarf running purely on proton decay, according to Adams and Laughlin's estimate, would generate something like 400 watts of power. That's enough to run a few household light bulbs from an entire dead star. Now, it's worth pausing here, because this is exactly the kind of claim that deserves a fact check rather than blind acceptance. And here's the honest answer. Proton decay has never actually been observed. Not once. It's a prediction made by certain grand unified theories in particle physics. Theories that try to tie the fundamental forces of nature together into one framework. But it remains just that, a prediction. The leading real-world search for it happens at a massive underground detector in Japan called Super Kamiokande, essentially a giant tank of ultra-pure water watched by thousands of sensitive light detectors, waiting for the telltale flash that a decaying proton would produce. Decades of watching, and Super Kamiokande has found nothing. What it has done instead is push the lower limit on the proton's lifetime higher and higher. Current published limits put the proton's lifetime at more than 2.4 times 10 to the 34th years for one possible decay pathway, and more than 1.6 times 10 to the 34th years for another. To put that in perspective, the universe itself is only about 1.38 times 10 to the 10th years old. These numbers are so large, they stop feeling like numbers and start feeling like a statement about how patient the universe is willing to be. So when a documentary tells you protons will eventually decay, what it should really be telling you is that some of our best theories predict they will, and we haven't proven it wrong yet, but we also haven't proven it right. It's an open question, not a settled fact, and treating it as settled would be dishonest. Assuming that prediction does hold, though, the end of the degenerate era leaves the universe with far less ordinary matter than it started with, and sets the stage for era number 4, the black hole era. By this point, black holes are essentially the last significant objects left standing, because unlike white dwarfs and neutron stars, black holes aren't destroyed by proton decay. They have a different, much stranger method of dying, one predicted by Stephen Hawking. In 1974, building on earlier work by Soviet physicists Yakov Zeldovich and Alexei Starobinsky, and by physicist Jacob Bekenstein, Hawking published a paper in the journal Nature titled, simply, Black Hole Explosions. In it, he showed, using quantum theory combined with general relativity, that black holes should very slowly radiate particles and lose mass over time, a process now known as Hawking radiation. The basic idea, stripped down, goes something like this. Empty space isn't actually perfectly empty. Even a total vacuum is constantly producing tiny pairs of particles that flicker in and out of existence almost instantly. Right at the edge of a black hole's event horizon, occasionally, one particle from a pair falls in while its partner escapes outward, and from a distance, it looks exactly as if the black hole itself spat out a particle. Do that enough times, over an unimaginable stretch of time, and the black hole slowly bleeds away its own mass. It's worth being clear about something here too. Hawking radiation has never been directly observed coming from a real, astrophysical black hole. The predicted signal is so unbelievably faint for anything of stellar mass or larger that we simply don't have the tools to detect it yet. It remains a theoretical prediction, one built on well-established physics that most physicists take very seriously, but it hasn't been confirmed by observation. That distinction matters. It's worth remembering too that even the basic existence of black holes wasn't something physicists always took for granted, not even Hawking himself. Take Cygnus X1, a bright X-ray source about 7,200 light-years away, first picked up by instruments on a suborbital rocket back in 1964. By the early 1970s, evidence was mounting that it might be the very first confirmed stellar mass black hole ever found. But the idea was still controversial enough that in 1974, Hawking made a friendly wager with fellow physicist Kip Thorne, the same Kip Thorne who would later share the Nobel Prize for detecting gravitational waves, betting that Cygnus X1 was not actually a black hole. It sounds backwards until you hear Hawking's own explanation for it. He called it his insurance policy. He'd spent so much of his career on black hole physics that if they turned out not to exist, at least he'd have the small consolation of winning a bet. By 1990, the observational evidence had piled up so thoroughly that Hawking finally conceded, reportedly having colleagues break into Thorne's office at Caltech while Thorne was out of town, just to leave a signed concession waiting for him. Even the man whose entire theoretical framework depended on black holes being real spent over a decade, formally, publicly, betting against them, just to hedge his own bets against the universe. If Hawking radiation is correct, though, the timescales involved for it to actually finish off a black hole are almost impossible to hold in your head. A black hole with the same mass as our Sun would take somewhere on the order of 10 to the 64th to 10 to the 67th years to fully evaporate, depending on which calculation you're looking at. A supermassive black hole, the kind that sits at the center of large galaxies, weighing in at around 100 billion times the mass of the Sun, would take roughly 10 to the 100th power of years, a number so large it's been nicknamed a googol. And some of the largest possible black holes, ones that could theoretically keep growing as entire superclusters of galaxies collapse inward over unimaginable timescales, might reach masses around 10 to the 14th solar masses, and take up to roughly 10 to the 106th power of years just to fade away completely. Yale astrophysicist Priyamvada Natarajan put it about as plainly as it can be put. Compared to those numbers, the entire current age of the universe is a rounding error. As far as we're concerned, she says, it's eternity. And there's one more twist buried inside that process. As a black hole shrinks through Hawking radiation, it doesn't cool down and fade quietly. It actually heats up. The smaller it gets, the hotter it becomes, and the hotter it becomes, the faster it radiates away its remaining mass, which makes it shrink even faster, in a runaway feedback loop that eventually ends in one final, catastrophic burst before the black hole disappears entirely. It's a strange kind of death for something we usually think of as the most permanent, unstoppable object in the universe. Even black holes, it turns out, are not forever. There's a deeper thread connecting all of this back to that word we spent time on earlier, entropy, and it's worth pulling on before we move any further. In the early 1970s, a physicist named Jacob Bekenstein made a proposal that struck a lot of his colleagues, including Hawking himself at first, as strange. Black holes, he argued, must carry entropy of their own, and that entropy isn't determined by how much stuff is packed inside, the way it would be for ordinary matter, but by the surface area of the event horizon itself. Hawking initially pushed back, arguing that without some way for a black hole to actually emit anything, it couldn't have real thermodynamic properties at all. Then Hawking did the math on his own radiation idea and ended up proving Bekenstein right, arriving at an almost unbelievably clean formula. A black hole's entropy works out to exactly 1/4 of the area of its event horizon. The reason any of this mattered in the first place traces straight back to that same second law of thermodynamics Clausius wrote down in 1865. Without black hole entropy, you'd have a loophole, a way to cheat the entire law. Just throw something disordered into a black hole, and its entropy would seem to vanish from the universe entirely. Bekenstein's insight closed that loophole, but it opened up a much stranger one in its place, a puzzle physicists still haven't fully solved, called the black hole information paradox. If a black hole eventually evaporates away completely, as Hawking's own math says it should, what happens to all the information about everything that ever fell into it? Every atom, every structure, every pattern. Basic quantum mechanics says information can never actually be destroyed. Not really. But Hawking's original calculations suggested the radiation leaking back out is essentially random noise, carrying nothing about what went in. If that's true, information really would be lost forever, which breaks one of the most fundamental rules in physics. As of right now, this remains a genuinely open problem, one of the most famous unsolved questions in all of theoretical physics. Though recent decades of work involving quantum entanglement have offered some promising, if still unfinished, ways it might get resolved after all. Once the very last black hole has evaporated away, somewhere out past 10 to the 100th years, and likely much further out than that for the largest ones, the universe crosses into its fifth and final chapter in Adams and Laughlin's framework, the Dark Era. By this point, there is nothing left resembling a star, a planet, or even a black hole. What remains is an extraordinarily thin, cold scattering of photons, neutrinos, electrons, and their antimatter counterparts, positrons, drifting through a universe that has expanded to a scale that makes today's observable universe look like a rounding error. Every so often, across almost unfathomable stretches of empty time, a wandering electron and a wandering positron might happen to find each other and briefly form a fragile, short-lived structure called positronium, before annihilating each other in a tiny flash and returning to drifting nothingness. That, as far as current physics can predict, is essentially the last kind of event the universe has left to offer. This entire slow slide, from a universe packed with stars, to a universe of dead stellar remnants, to a universe of evaporating black holes, to a universe of scattered drifting particles, is often summed up by physicists using the term heat death. It's an important distinction to make clearly. Heat death doesn't mean the universe gets cold in the way a room gets cold. Temperature actually keeps dropping toward, but never quite reaching, absolute zero, as everything spreads farther and farther apart. What heat death really describes is a state of maximum entropy, meaning maximum disorder, where there's no longer enough of a difference in energy from one place to another to do any kind of work, or to power any kind of process, or to build any kind of structure. No stars, no chemistry, no life, just a smooth, dilute, directionless nothing, everywhere, forever. And it's worth noting that even this picture isn't fully settled science. Physicists are still working out exactly how to quantify something called gravitational entropy, and that gap in our understanding means the fine details of this final state aren't as locked down as the broad outline suggests. That word, entropy, deserves a moment of its own, because it's carrying an enormous amount of weight in this story, and it's a lot older than anything else we've talked about tonight. It didn't come from a cosmologist. It came from a German physicist named Rudolf Clausius, who coined it in 1865, borrowing from a Greek word that roughly means transformation. Clausius wasn't thinking about black holes or the death of the universe. He was thinking about steam engines, heat, and the industrial machinery of his own century, working out why energy always seems to leak away into less useful forms whenever anything actually happens. By the time he was finished, he had boiled the entire second law of thermodynamics down to 2 sentences. The energy of the universe is constant, and the entropy of the universe tends toward a maximum. A few years later, an Austrian physicist named Ludwig Boltzmann took that idea further, showing mathematically why entropy keeps increasing in the first place. It comes down to simple odds. There are vastly more ways for a system to be disordered than there are for it to be neatly arranged. So left alone, over time, any system will almost always drift toward whichever state has the most possible ways of existing, which just happens to be the messy one. Clausius himself, writing in the 1860s, already understood exactly where this logic pointed, if you let it run long enough, toward a universe that gradually loses the ability to do anything at all. The term heat death, anchoring the entire second half of this video, isn't some invention of modern cosmology. It's 160 years old, first written down by a man thinking about steam pistons, decades before anyone had ever heard of a galaxy, let alone a black hole. So why does any of this even happen? Why does the universe keep expanding forever, instead of eventually collapsing back in on itself, the way earlier generations of physicists once assumed it would? Before we get to that answer, there's one loose thread worth tying up, because it loops all the way back to something we mentioned near the very beginning of this video, the Chandrasekhar limit, that ceiling of about 1.5 times the Sun's mass that determines whether a dying star's core settles down as a quiet white dwarf or gets crushed into something more extreme. It turns out that same exact number is also the trigger behind one of the most useful explosions in all of astronomy. Picture a white dwarf that isn't alone, one that has a companion star close enough to slowly feed it material over time, matter drifting off the companion and piling onto the dead star's surface. As the white dwarf accretes that extra mass, it doesn't grow the way you'd expect. Remember, white dwarfs get smaller as they get heavier, so it shrinks and compresses further, its interior growing hotter and denser the closer it creeps toward that Chandrasekhar ceiling. When it finally gets there, something extraordinary happens. A runaway nuclear reaction ignites almost simultaneously throughout the entire star, fusing carbon into iron and nickel in what amounts to the whole white dwarf detonating at once. Astronomers call this a Type 1a supernova, and it means a star that already died once, quietly, as a white dwarf, can still go out with a second, far more violent death later on, if it happens to have the right neighbor. Scientists are still debating some of the finer details, whether the fuel always comes from an ordinary companion star, or sometimes from 2 white dwarfs merging directly into each other. But here's the detail that actually matters for the rest of this story. Because that explosion always gets triggered at essentially the same mass, the Chandrasekhar limit, every single Type 1a supernova explodes with almost exactly the same peak brightness, no matter where in the universe it happens. That consistency is what turns them into what astronomers call standard candles, reliable enough that you can use their brightness to measure distance across billions of light years, the exact tool that's about to become the centerpiece of this next part of the story. Now, to actually answer the question of why the universe keeps expanding forever, instead of eventually collapsing back in on itself, we need to back up nearly 70 years earlier than you'd expect, to 1929, because that's when astronomers first figured out the universe was expanding at all. An astronomer named Vesto Slipher, working at the Lowell Observatory in Arizona starting around 1912, had spent years patiently measuring something called redshift in the light coming from distant spiral nebulae, what we'd now call other galaxies, essentially a stretching of light toward longer, redder wavelengths that happens when an object is moving away from you, the same basic principle as a siren dropping in pitch as an ambulance speeds past and away. By 1923, working with a single 24-inch telescope, Slipher had measured this effect in 41 different galaxies, and 36 of them were moving away from us, one of them at close to 1,800 kilometers per second. Then, working at Mount Wilson Observatory in California, with his assistant Milton Humason, an astronomer named Edwin Hubble combined Slipher's redshift measurements with his own separate distance measurements, and on January 17, 1929, he announced something that overturned centuries of assumption. The universe wasn't static and unchanging. It was expanding, and the farther away a galaxy was, the faster it was rushing away from us. That relationship is still called Hubble's law today, even though historians of science now generally agree that Slipher's decade of patient, underappreciated groundwork deserves just as much credit, so much so that some have suggested Hubble's famous graph should really be called the Hubble-Slipher graph instead. For nearly 70 years after that, the assumption among physicists was straightforward. The universe was expanding, sure, but gravity, the combined pull of every galaxy on every other galaxy, should be slowly putting the brakes on that expansion, the same way gravity eventually pulls a ball back down after you throw it in the air. Nobody seriously expected anything else. And then, in 1998, that assumption fell apart completely. Two separate teams of astronomers, working independently and in friendly competition with each other, were studying a very specific type of exploding star called a Type 1a supernova. These supernovae are useful because they tend to explode with remarkably consistent brightness, which lets astronomers use them as reliable distance markers, sometimes called standard candles, across billions of light-years of space. One team, the Supernova Cosmology Project, was led by Saul Perlmutter and had been working on this since 1988. The other, the High Z Supernova Search Team, was led by Brian Schmidt, with Adam Rees serving as lead author on their landmark findings. Both teams expected to find that the universe's expansion, driven by the momentum of the Big Bang, was gradually slowing down over time, the way gravity should be pulling everything back together. Instead, both teams found the opposite. The most distant supernovae were coming out about 25% fainter than expected, which meant they were farther away than a slowing, decelerating universe could explain. The universe wasn't just expanding, it was expanding faster and faster, accelerating, and nothing in the standard physics of the time predicted that should be happening. The discovery was named Breakthrough of the Year by the journal Science that same year, and it forced physicists to accept the existence of something they couldn't directly see or explain, a mysterious, repulsive force now called dark energy, one that appears to make up somewhere around 73% of everything in the universe by mass and energy, based on estimates from around the time of the Nobel announcement. In 2011, Perlmutter, Schmidt, and Rees were jointly awarded the Nobel Prize in Physics for the discovery, with Perlmutter receiving half the prize and Schmidt and Rees sharing the other half. And here's the honest, slightly unsatisfying truth that deserves to be said plainly. We still don't know what dark energy actually is. Physicists openly describe it as one of the single biggest open problems in all of 21st century physics. We know it's there because of what it does to the expansion of the universe. We have no confirmed explanation for what it actually is. And here's where it gets even more interesting. Because everything we've walked through so far, the degenerate era, the black hole era, the dark era, the slow slide into heat death, all of it assumes one specific thing about dark energy, that its strength stays exactly the same forever, a fixed, unchanging property woven into empty space itself. Physicists call this a cosmological constant, and right now, it's the version of dark energy best supported by the evidence we have. But because nobody actually knows what dark energy is, physicists have never been able to fully rule out a couple of very different endings. If dark energy were to grow stronger over time instead of staying constant, the universe wouldn't just cool down and thin out the way we've described. It would eventually tear itself apart directly, in a scenario physicists genuinely call the Big Rip. The accelerating expansion would eventually overpower not just the gravity holding galaxies together, but the electromagnetic force holding atoms together, and even the nuclear forces holding the particles inside atoms together. Galaxies would shred first, then solar systems, then planets, then the atoms in your own body, torn apart from the inside out by the expansion of space itself. And on the opposite end, if dark energy were to weaken over time, or even reverse entirely, gravity could eventually win back control, halting the expansion and pulling everything back down into a collapse, a mirror image of the Big Bang, sometimes called the Big Crunch. Some physicists have speculated, purely as a hypothesis with no confirming evidence, that a Big Crunch might not be a true ending at all, but a big bounce, a collapse that triggers a brand new Big Bang and starts the entire cycle over again. That idea remains firmly speculative. Nobody has any actual evidence pointing toward it. For a long time, most of the evidence pointed cleanly toward the version of dark energy that never changes, which is exactly the assumption baked into every one of the 5 eras we just walked through. But that assumption has started to wobble, and it's happened extremely recently, close enough to right now that it's still developing as we're putting this together. In April of 2024, and again with an expanded dataset in 2025, a massive sky survey instrument called DESI, the Dark Energy Spectroscopic Instrument, which is capable of observing 5,000 galaxies at once, released results hinting that dark energy might not be constant after all. Looking back across roughly 11 billion years of cosmic history, the data suggested dark energy might actually be getting weaker over time, becoming, in the words of the scientists involved, less pushy. It's not confirmed. The researchers themselves are careful to call it a hint, not a discovery, based on just the first year or two of data from a survey designed to run for 5. But Adam Rees, one of the 3 scientists who won that 2011 Nobel Prize for discovering dark energy in the first place, responded to the news with a sentence that tells you exactly how seriously physicists are taking it. If it holds up, he said, this is a very big deal. So even the ending of this entire story, the one we're about to walk through in detail, comes with an asterisk. The heat death scenario is where the evidence currently points. It is not yet where the evidence has definitively landed, but whatever dark energy turns out to be, its effect reaches much further than just the slow death of stars and galaxies. And this next part might be the strangest idea in the entire video. Because space itself is expanding faster and faster, there's a maximum distance, called the cosmic event horizon, beyond which light will simply never be able to reach us again, no matter how long we wait. Not because the light isn't traveling toward us, it is. It's because the space between that light and us is stretching faster than the light can cross it, like trying to walk toward a doorway on a floor that's expanding faster than you can move. And here's the part that should genuinely unsettle you. This isn't only a future problem. Right now, tonight, an estimated 94% of the universe already lies beyond our reach forever, permanently unreachable even in principle, even if you could somehow travel at the speed of light starting this very second. 2 physicists, Lawrence Krauss and Robert Scherer, worked out exactly where this leads in a 2007 paper with a blunt, almost ominous title, The Return of a Static Universe and the End of Cosmology. Their conclusion was this: as the accelerating expansion continues, more and more distant galaxies will cross that cosmic event horizon and vanish from view, not by exploding or being destroyed, but simply by redshifting and fading until their light can no longer reach us at all. Over roughly the next 100 billion years, and decisively so within a few trillion, essentially every galaxy outside our own local group, the small, gravitationally bound cluster that includes the Milky Way and Andromeda, will slip past that horizon for good. What stays behind, held together tightly enough by its own gravity to resist the expansion, is just us, our own galaxy, merged together with Andromeda and its smaller neighbors into one single galaxy, surrounded by a sky that has gone completely, permanently empty of everything else. Physicist Brian Greene once summed up the strangeness of this in a single sentence. In the far future, he said, everything we now see, except for our own local galaxy, will have disappeared from view, and the entire visible universe will effectively vanish before our eyes. And Krauss and Scherer took that idea one devastating step further. A civilization that happened to evolve far enough in the future, looking up at a sky containing nothing but one static, unmoving galaxy, would have absolutely no way, using any telescope, any instrument, any observation, of ever discovering that the universe used to be expanding at all. No way of finding the cosmic microwave background, since it will have redshifted into complete undetectability by then too. No way of finding the evidence for a Big Bang. The very proof that let 20th century astronomers piece together the story we're telling you right now will have quietly, permanently vanished from the sky, long before those future observers ever existed to look for it. They would build their physics, their cosmology, their entire picture of reality around a universe that looks static and eternal, and they would have absolutely no reason to suspect otherwise, because the evidence wouldn't just be hidden, it would be gone. Which brings up a strange, almost uncomfortable question to sit with before we wrap this up. If the universe really is this vast, this old, and this thoroughly littered with the remains of dead stars, dead galaxies, and dying black holes, where is everybody else who might have once looked up at their own version of this sky? Back in the summer of 1950, the physicist Enrico Fermi was walking to lunch at Los Alamos National Laboratory with a few colleagues, having just finished a conversation about flying saucers and whether faster-than-light travel might ever be possible. The topic had already drifted on to something else entirely by the time the group sat down to eat, when Fermi, apparently out of nowhere, asked a simple question that his colleagues remembered slightly differently, but that has haunted physics and astronomy ever since. Where is everybody? He wasn't asking about lunch. He was doing rough math in his head about the sheer number of stars in our galaxy, something on the order of 100 to 400 billion of them. The age of that galaxy, well over 10 billion years, and the amount of time any advanced civilization would have had to spread outward from wherever it started. Even at slow, unglamorous travel speeds, Fermi's back-of-the-napkin numbers suggested the galaxy should have been thoroughly explored, settled, or at least visited by now, many times over. And yet, as far as we can tell, in a universe already this saturated with the remains of dead stars, nobody has ever shown up. No signal, no visit, no unambiguous trace. This has become known as the Fermi paradox, and more than 70 years later, it remains completely unresolved. It's not for lack of trying either. 10 years after Fermi's lunchtime question, in the spring and summer of 1960, a young radio astronomer named Frank Drake pointed an 85-foot dish at the National Radio Astronomy Observatory in Green Bank, West Virginia, toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani, both roughly 11 light-years away, and simply listened. He tuned the receiver to a very specific frequency, the one naturally emitted by hydrogen atoms drifting through space, on the logic that any sufficiently advanced civilization would recognize that exact frequency as a kind of universal constant, a number written into the physics of the universe itself, and might use it to say hello. He called the project Ozma, after a princess from the land of Oz. Over about 150 hours of listening, spread across 4 months, Drake heard nothing except static, and one false alarm that turned out to be a passing aircraft. It was, by any measure, a quiet, almost anticlimactic experiment. But it was also the very first time humanity had deliberately, systematically pointed an instrument at the stars and asked, out loud in radio waves, if anyone was home. A year later, gathering a small group of scientists, including a young Carl Sagan, to discuss what a search like that would actually require, Drake sketched out a simple equation on a chalkboard, multiplying together a handful of factors: the rate new stars form, the fraction with planets, the fraction of those that might host life, intelligence, technology, and communication, and the length of time any civilization might keep broadcasting before it either destroys itself or simply moves on. That formula is still called the Drake equation today, and here's the honest part. Several of its key variables remain completely unknown, even now, more than 60 years later. The equation doesn't solve the Fermi paradox. It just gives the uncertainty a shape you can write down. In 1974, Drake helped design and transmit an actual message outward, a burst of 1,679 binary digits, beamed from the newly upgraded Arecibo telescope in Puerto Rico toward a distant globular cluster called M13, roughly 25,000 light-years away. That message is still traveling. It hasn't arrived yet. It won't arrive for another 23,000 years or so. If anyone out there eventually receives it and decides to write back, the reply won't reach us for another 25,000 years after that, which means humanity's first deliberate attempt at a conversation with the rest of the universe is a message that won't even finish being asked until long after everyone who sent it is gone. There's a framework worth knowing about here too, because it sharpens exactly how strange this silence really is. Back in 1964, a Soviet astrophysicist named Nikolai Kardashev proposed a simple way to rank hypothetical civilizations, not by culture, not by intelligence, but by raw energy. How much of it a civilization could actually get its hands on and use. He called a civilization Type 1 if it could harness all the energy available on its home planet. Type 2 if it could harness the entire output of its home star, something on the order of 10 to the 26th watts. Type 3 if it could somehow harness the combined energy resources of an entire galaxy. Carl Sagan later refined the scale with decimal gradations, and by his own 1973 estimate, human civilization sat at only about 0.7 on that scale, meaning we haven't even fully mastered our own planet's energy yet, let alone our star. More recent estimates put total human energy use at around 18 terawatts, roughly 1,000 times below what would even count as Type 1. And here's what makes that scale relevant to everything else in this video. A civilization that reached Type 2, one merely capable of using the full output of a single star, should, in principle, be detectable from staggering distances away, its energy signature standing out against the natural background of the galaxy. A Type 3 civilization, wielding an entire galaxy's worth of energy, should be almost impossible to miss. And yet, across every survey, every radio search, every instrument we've ever pointed at the sky, there's no confirmed sign of either one. Not a whisper. Maybe intelligent life really is exceedingly rare. Maybe civilizations tend to be short-lived, for reasons we'd rather not think too hard about. Maybe interstellar distances really are as forbidding as they look from here. Or maybe we simply haven't looked long enough, or in the right way, yet. Nobody knows. What we do know is this. The same universe that is slowly, patiently filling up with graveyards is, as far as our instruments can currently tell, remarkably quiet. We are, for now, the only ones we know of standing at the edge of it, looking in. Before we close this out, there's one more idea worth mentioning, and it needs to come with a clear label attached. This next part is speculative, not settled science, and it's important to treat it that way. Back in 1980, physicist Alan Guth proposed something called cosmic inflation, an extraordinarily brief, extraordinarily fast period of expansion in the very first fraction of a second after the Big Bang, an idea that's now a well-supported part of mainstream cosmology because it successfully explains several features of the universe we actually observe. But a few years later, working independently, physicists Andrei Linde, along with Paul Steinhardt and Alexander Vilenkin, pushed that idea somewhere much stranger. What if inflation, once it starts, never actually stops everywhere at once? What if most of space just keeps inflating forever, endlessly, while only certain isolated pockets locally break off, cool down, and settle into ordinary universes, each one potentially with its own separate physical constants, its own separate laws, its own separate version of everything we've just spent this entire video describing? Under that picture, sometimes called eternal inflation, our own Big Bang wouldn't be the beginning of everything. It would just be the moment our particular pocket happened to break away from a much larger, endlessly bubbling background. One bubble among an unknown number of others, collectively referred to as the multiverse. Alan Guth himself has put it plainly. According to this view, our observed universe, as vast as it seems, is only an infinitesimal fraction of everything that actually exists. And here's the honest caveat that has to come with that idea. The reason it's being mentioned last and clearly separated from everything else in this video. This remains genuinely speculative. Some physicists studying it openly admit that the existence of other bubble universes may not be testable, not now, not ever, even in principle, which is exactly the kind of statement that makes other scientists uncomfortable calling it a scientific theory at all. If it's true, then everything we've just spent this entire video walking through, the dead stars, the evaporating black holes, the slow slide into heat death, might only be the story of one single universe out of an uncountable number of others, each one quietly running its own version of this same story, or possibly a completely different one, forever, somewhere we will never be able to see or measure or confirm. There's one last piece of this puzzle, and it's older than every single discovery we've talked about so far, dating back centuries before Hubble, before Gaia, before anyone had ever heard of a black hole. It's a simple question, the kind a curious person might ask without any training in physics at all. If the universe really is full of stars, spread out in every direction, then why is the night sky dark? Think about it the way early astronomers eventually had to. If you look in any direction, and the universe genuinely goes on more or less forever, filled more or less evenly with stars, then your line of sight should eventually hit a star no matter which way you're facing, the same way a line drawn through a sufficiently thick, endless forest should eventually hit a tree, no matter what angle you pick. If that's true, then every single point in the sky should be glowing as brightly as the surface of the sun. The whole sky, not just the stars themselves, should be blazing, all the time, day and night. It obviously isn't. This is Olbers' paradox, named for the German astronomer Heinrich Olbers, a former physician who took up astronomy as a serious second calling and wrote about the problem in 1823, though the puzzle itself goes back even further, to Johannes Kepler in the early 1600s, and an English astronomer named Thomas Digges before that. For centuries, people tried to explain it away. Maybe dust blocks the distant starlight, some suggested. But that doesn't actually work, because given enough time, that dust would absorb so much starlight that it would eventually heat up and start glowing too, right back into the same problem. It took until the 20th century for anyone to land on the actual answer, and the actual answer turns out to be the entire subject of this video, condensed into a single sentence. The night sky is dark because the universe had a beginning, and light only travels so fast. We can only ever see stars whose light has had enough time to physically reach us since that beginning, roughly 13.8 billion years ago, which means the vast majority of whatever else might be out there, in an unimaginably large or even infinite universe, simply hasn't had time to arrive yet. And what little light has made the whole journey from the very edge of what we can see, the ancient afterglow of the Big Bang itself, has been stretched by the universe's own expansion into wavelengths our eyes were never built to detect, the same faint microwave hum that Penzias and Wilson stumbled onto by accident while chasing pigeons out of an antenna. The darkness between the stars isn't emptiness, it's evidence. It's the same expanding, aging, finite universe described in every single fact in this video, silently written across the sky, in the one thing you'd never think to question, the color black. So let's bring this back down to Earth, quite literally. Right now, tonight, if you step outside and look up, you're looking at a sky that already contains dead stars scattered among the living ones, black holes hiding in plain sight because they emit no light at all, rogue planets drifting between the stars with no sun to call their own, and the faint, frozen afterglow of the Big Bang itself, discovered by two men who thought pigeons were to blame. Somewhere out there, a neutron star discovered by a graduate student staring at chart paper is still blinking, precisely, patiently, the way it has for who knows how long before we ever noticed. Somewhere much, much farther out, light left over from a black hole that formed 400 million years after the Big Bang is still arriving, having spent 13 billion years crossing the universe just to reach a mirror on a telescope. And somewhere past the edge of our own solar system, two small machines built by human hands in 1977 are still drifting outward, slowly losing power, on a trajectory that could carry them through trillions of years, long after everything else in this story has already happened. You're looking at a sun that is, right now, at this exact moment, roughly halfway through its own life, already on a slow, quiet, 10 billion year path toward becoming a literal crystal. The Milky Way itself is estimated to hold something like 100 million black holes, almost all of them completely invisible to us, discovered only by the subtle way they tug on stars we can actually see. Our galaxy may or may not collide with Andromeda, a question that used to seem settled and now genuinely isn't. And somewhere out past all of that, on timescales so enormous they stop being relatable numbers and start being philosophical statements, the entire universe is slowly, quietly, inevitably making its way toward becoming exactly what the title of this video suggested, a graveyard. Not a dramatic one, not an explosive one, just an extraordinarily patient one. One white dwarf, one dead galaxy, one evaporating black hole, and one vanishing horizon at a time. There's one more image worth leaving you with, and it comes from the same spacecraft we've already spent so much time on tonight. On February the 14th, 1990, at Carl Sagan's own suggestion, Voyager 1 turned its camera around one last time, from about 6 billion kilometers away, already well past Neptune, and took a photograph looking back at where it came from. In that photograph, Earth isn't a blue marble, isn't a globe, isn't even a full pixel. It shows up as a fraction of one, a crescent of light measuring about 12/100ths of a single pixel, caught almost by accident inside a scattered band of sunlight. 34 minutes after taking it, Voyager 1 powered its cameras off for good, to save what little energy it had left for the decades of drifting still ahead of it. Sagan later called it the pale blue dot, and the phrase he's most remembered for, looking at that image, was simple: that's here, that's home, that's us. Every person who has ever lived, every war and every discovery, and every single fact in this entire video happened on that one point of light, smaller than a pixel, photographed by a machine that is, right now, still out there, still carrying a golden record with a stranger's heartbeat and a child's hello on it, still headed toward a future so long that the 13.8 billion years behind us wouldn't even register as a rounding error against it. Earth is already inside that graveyard. It has been the whole time. We just usually call it something else. We call it the night sky.